And that's going to be very important later on. This is a trans double bond. Then afterwards, we add water. So, oh, by the way, because this reaction is an oxidation reaction, it should not be surprising that the enzyme name is a dehydrogenase. Then the next step, we add water. So we call that a hydratase. And the whole point of adding water is that we added oxygen to the molecule. And whenever oxygens exist in the molecule, there's opportunity for more oxidation. So here we add a water so that it becomes alcohol. So this becomes hydroxyacyl-CoA. What's important now is that when you see this OH group, you should probably think, I can turn this into a carbonyl and oxidize it one more time. And so that's exactly what happens next. We take this alcohol and oxidize it into a carbonyl. So something must get reduced. And so in this case, NAD positive gets reduced to NADH. And it should be no surprise to you, an oxidation reduction reaction is named dehydrogenase. Beta hydroxyacyl-CoA dehydrogenase. So now you're left with this group here where you have two carbonyls present in the molecule. And so this is where a special reaction happens then, where acetyl-CoA comes in and attacks this carbonyl. And if this carbonyl gets attacked, the carbonyl swings up, the electrons swing up, and then eventually it will come back down again. And when it comes back down again, it kicks out the CH2. And so effectively, this is a substitution reaction where coenzyme ASH comes in and acetyl-CoA leaves. And so what you're left with is a new coenzyme A attached, but 14 carbons long now instead of 16, and that free acetyl-CoA is out. So this process is a couple steps, but I like to remember it as follows. It is an oxidation, followed by hydration, followed by oxidation, followed by substitution. And so hopefully you should view it this way. Not super important to memorize the enzyme names. You can probably infer them, but you should remember it as this so that you are hopefully capable of remembering then that what do you get from this reaction is an FADH from that oxidation, an NADH from the other oxidation, and then an acetyl-CoA after that substitution reaction. So in every single time we remove two carbons, we produce FADH2, we produce NADH, and we produce acetyl-CoA. So hopefully that is something you remember for accounting, in terms of accounting for energy from a fat breakdown. So in that scenario, if we have a 16 carbon long palmitate, then it should remind you that you're gonna repeat this process. So if there's 16 carbons of palmitate, I like to think of that as 8 times acetyl-CoAs. And there is 7 bonds in between them. So that means 7 reactions of fatty acid breakdown, which would tell me that as I break down the 17 carbon palmitate into acetyl-CoAs, I will produce 8 acetyl-CoAs, 7 FADH2s, and 7 NADHs. So hopefully that reaction is relatively straightforward. And then hopefully you'll remember from the TCA cycle what each acetyl-CoA does in the process. Okay, so now let's move on to the maybe weird examples. So odd numbered, what do we do with that? And so usually when you have an odd numbered fatty acid, you continue the process until the end, where your final product, instead of a 2-carbon acetyl-CoA is the 3-carbon acetyl group, and we call that propionyl-CoA. So propionyl-CoA is digested differently. So what we do is we first carboxylate this molecule. And so if you remember from the last unit, when a carboxylation reaction happens, for example, pyruvate to oxaloacetate, you need a specific cofactor, and that's biotin, and ATP, and bicarbonate. So those three. So we use those three to add another carboxyl group to propionyl-CoA and make it methyl-malonyl-CoA. That's the first step. Then the next step we do is we use an epimerase to switch between this CO2 group and this acetyl-CoA group. We swap them together, and because they're happening at the same carbon, you can think of this as switching stereoisomers. And switching stereoisomers is an epimerase reaction. So that's what happens on the next step. And then this next reaction, we swap between two components. And hopefully that for you reminds you of a mutase reaction. So methyl-malonyl-CoA mutase swaps those two. And the only thing that's unique about this one is that this reaction needs coenzyme vitamin B12. So remember, if you're doing a methyl-malonyl to succinyl-CoA reaction, you need vitamin B12. But what you should notice is that we don't produce acetyl-CoA in the end of this whole reaction. Instead, what we get is we turn propionyl-CoA into succinyl-CoA. So this part then enters the TCA cycle. But instead of entering like acetyl-CoA, where it has combined with a citrate, this succinyl-CoA is actually just entered midway through the TCA cycle. And so this is particularly useful. But also another thing you should notice, succinyl-CoA can be turned to oxaloacetate via the TCA cycle, and then this oxaloacetate can be turned into a sugar. And so we said that fatty acids can't be turned in, acetyl-CoA cannot be turned back into a sugar unless you consume something else. But actually, if you have an odd numbered fatty acid, it might be the succinyl-CoA that is possible to turn into a sugar because it is an intermediate in TCA cycle. So hopefully you are thinking about that when you hear the word succinyl-CoA, because it is a part of the TCA cycle. One thing to note is that you do consume ATP at this step. So if you ever have to do an accounting step, you want to remember the ATP cost for this process. Then the next question is, what if there's a saturation? So the first thing I want to start with is that saturations in double bonds in the fatty acid are usually cis. And because usually the enzymes that produce the unsaturation produce cis double bonds. And therefore we have the enzymes to break down cis double bonds. For trans fats, where the fat itself has a trans double bond, we typically don't have the enzyme to break that down. And so hopefully, usually we have a hard time breaking those down. And that's why they say trans fats are bad for you. So let's start with this example here, oleo oil CoA. In this case, when we have a double bond in the middle, the process stays the same up to that part. And so in this case, beta oxidation occurs normally, and we get rid of 3 acetyl-CoAs until eventually we run into the double bond. And usually when we have a cis double bond and it's perfectly natural, the double bond should line up perfectly between the beta and the gamma carbons of the double bond. So remember, if we base it off the carbonyl, this is the alpha carbon, this is the beta, and this is the gamma. So usually it lines up perfectly in the beta gamma, or for biochemists, they like to call it the 2 and 3. So once you have the double bond lined up in 2 and 3, what we're gonna do is isomerize it into a trans double bond. And so that's done by what's called enoyl-CoA isomerase. The mechanism for this is not super important, but basically what they're doing is converting it from a cis double bond to a trans double bond. And so once you're at this step, you should hopefully realize that A trans double bond in the 1 and 2 position is the exact intermediate that we saw when we did beta oxidation earlier. We had a 1,2 double bond that is trans. And so this is actually just the intermediate. This is actually just the intermediate of the normal beta oxidation process. And so this then will get oxidized by NADH. So I'm going to create a separate pathway. This will we'll add water to it using hydratase, and then we'll oxidize it to form NADH, and then we'll get rid of acetyl-CoA, and we get the rest of the fatty acid. And so this will then now enter the normal beta oxidation process afterwards. But the one key difference here is that when we turned a normal fatty acid into a trans double bond containing fatty acid, we generated an FADH2. In this process, because there's already a double bond, we don't generate an FADH2. So the only difference is that unsaturated fats afford less FADH2. So we don't need to form a double bond using FAD anymore, and so therefore we don't make as much FADH2. But the NADH production step still is present in this reaction. Okay, so to count again for energy, hopefully you guys remember when you have an oxidation reaction from an alkane to an alkene, that's an FADH2 producing reaction. If you have an alcohol to carbonyl producing oxidation, you produce NADH in the process. And here's another example. If you have an 18 carbon long fat, hopefully you should think of that as 9 units of acetyl-CoA. And if there's 9 of them and there's 8 bonds in between, and therefore we need to do beta oxidation 8 times. And so you need to multiply the products from one reaction by 8. And that is 1 FADH2 and 1 NADH. And then afterwards, usually we'll ask you to convert this acetyl-CoA back to CO2. So hopefully you guys remember what the energy production is of turning acetyl-CoA to CO2 using the TCA cycle. And I put in here a guide as well for the odd numbered fatty acids as well. So just to kind of summarize, what could we ask you about these fatty acid questions? We can ask you about naming. That's usually the most straightforward question with very little difficulty. We can ask you about the pathway as a whole. What products do we make from this pathway? What intermediates do we make? And how many steps is the process? We can ask you about how the mechanism for how the odd numbered fatty acids can be turned into sugars maybe, and how maybe the last step is converted, or just what steps or enzymes are necessary for the double bond. So just typical reactions that we've seen so far and how you should think about them. Just make sure you understand the cofactors necessary and make sure you understand what products are made from each step. So now we're then gonna transition to a different recitation topic, which is in this case, electron transfer chain. So I put it in here as recitation 11, but we're gonna cover it today for recitation 10. So to review that, let's cover a little bit about electron redox review. So when you have thermodynamics and we have delta G, we often remember that negative delta G values mean that the reaction is favorable or spontaneous. So typically the G or free energy of the reactants usually are greater than the products, and that means that the delta G is negative.